challenge with sequences and series is not that the math is hard. The math itself is easy. It's addition, multiplication, division, nothing fantastic. What's probably going to bug you more than anything here is all the symbols and notation to learn the rules. I am going to be eventually getting some formulas out of this. You do not have to memorize these formulas. I will be giving you these formulas. They are, however, required to be on that journal, so make sure they end up on there when we get to that point. But it'll be a little bit before I get to actual formulas. Okay, I'm going to hazard a guess. If I said name a sequence, you could probably give me an example of a sequence. Well, 1, 2, 3, 4, 5 is technically a sequence. It's not got a lot of pizzazz.
1, 2, 4, 6, 8, 5.
Okay, I heard 2, 4, 6, 8, 10. 5, 10, 15, 20. All right, give me
3, 6, 9.
Okay, give me something that's not the exact same kind of a pattern.
1, 3, 5, trapezoid.
1,
3, 5, 7.
That's still adding 2 every time.
Square, triangle, circle.
Oh, 0. Okay, 1, 3, 6. 3, 1, 6. What are you trying to?
You're adding 1.
Oh, you're adding. Okay, you're adding 1, adding 2, adding 3, adding 4 would be 10. Yes. Okay.
1, 2, 3, 5, 8. And keep going on.
13, 21.
Is that not as the bottom? No.
Yeah, she didn't get it up yet. I gotta get my poster up. Yes, that is known as. That's very famous. It's actually 1, 1. It has to start with a 1, 1. That is actually an extremely famous sequence known as the Fibonacci sequence. And nope, Italian. Fibonacci. Leonardo de Fibonacci. He was actually studying rabbit reproduction. Okay, and so he started out with 1 male and 1 female, and they could reproduce after 2 months, I think it was. So yeah, and so then he had 2 rabbits, but then they had a baby, so then they had 3 rabbits. And then when you start figuring out when the babies can have babies, and he had to do with how many total rabbits he had, he came up with this sequence. Yes. I have no idea on that score. I think he actually was a mathematician. He was wondering, I don't know how he got to wondering about this thing, but he discovered this sequence, and this sequence is extremely famous. I'm going to pause it. All right. It turns out the Fibonacci sequence is extremely common in nature. I don't know if these are strong enough magnets to hold them. They're not. Okay, never mind. They're not. Okay, lots of things, particularly things that grow in nature, have a Fibonacci number in them. You will discover if you start counting the number of petals in flowers, they'll have 3 petals, or 5 petals, or 8 petals, or 13 petals. Okay, why is a 4-leaf clover lucky? What's a normal clover have? 3. Why is 4 lucky?
Because it's not irregular.
It's irregular. It's unusual. Nature does not normally produce a 4-leaf clover. It's not in the Fibonacci sequence either. So if you count the rows of on pine cones, you count how many little pokey things in the pine cone, Fibonacci numbers. If you're crazy enough to count all the seeds of the sunflower, and count the rows, Fibonacci numbers. Look at the number of seeds in an apple. 5. And a lemon, they have 8 seeds. A starfish has 5 arms. You're crazy enough to once again count rows of pineapples, the little spiny things on a pineapple. All Fibonacci numbers. They kept finding out that these numbers kept showing up in nature. And so Fibonacci sequence is actually very famous. Probably if you're going to say name a sequence, it's the most famous sequence there is. Now, the question is, did we all see how they got it?
No.
1 and 1 add together make 2. 1 and 2 add together make 3. You add the previous 2 numbers to get the next number. So 2 plus 3 is 5. 3 plus 5 is 8. So what's the next number in this sequence?
21 plus 13.
21 plus 13, which would be 34. So 34 is the next number in the sequence. Very
Time out. Well, I know, I get the sequence. Why is everything in nature that way?
I don't have an answer for you why, but nature tends to follow, not perfectly, not every single thing, but tons of things tend to grow with and have Fibonacci number amount of things. As with the way, the rate at which things grow tended to be E as a base number. It's aliens, okay. Pi, why does pi have something to do with every single circle?
I don't know. Why does it? What the? I know.
Okay, well, the answer I want to give you, I'm not allowed to give you in school.
Say it.
I probably can give it to you in Seneca, Kansas.
Go ahead.
Yeah, God had a plan. Some far more brilliant than us.
Why can't you say this?
Oh, that's, yeah, this is a public school. I'm not allowed to talk religion with you. So.
Good thing. Can't you preach what you believe?
No, not, I can't in a public school. Yeah. I can only provide you factual information. Okay, so, in definition then, a sequence is simply a list of numbers. But the key factor is they have to follow some patterns. There's all kinds of patterns they can follow. But a sequence has to be a list of numbers that has a pattern to it. There's got to be a reason for how you can find that sequence and how you can get the next number down the sequence. Yes. Okay. Now, here we go. Remember I said the terminology is the symbolism that tends to get us a bit of an issue with sequences. I'm going to use the Fibonacci sequence here as my example. Okay. Each number in the sequence is called a term. So you have first term, second term, third term, fourth term, etc. Okay. They use the letter A to represent a term. I have no idea why they picked A. So to say this is the first term, we write A with a little 1 subscript to indicate first term. So second term is A sub 2. Third term is A sub 3. What's the next one? A subscript 4. Okay, now, then when we want to talk about some unknown term, we're going to be trying to find some unknown term down the road somewhere. Okay, since it's an unknown term, they call it A sub n. N could be any number. It could be the 10th term, the 100th term, the 3000th term. So that can represent your unknown term, or we also call it the last term, the last term in the sequence that you're looking for. So that's, you're going to see that in a lot of formulas. A sub n means the last term, the term where you're ending your sequence at. Now, here's where the distinction comes in. A's mean you're representing a term. Okay, how many terms you have, if I have 20 terms or 50 terms, that's n. N is the number of terms I have. So if you're talking about, they say find a sequence with 20 terms, then n's 20. You've got 20 terms in the list. You have to keep A sub n and n straight. Which one means which? Those are probably the two that cause the most issue. Okay, the ones you're going to see the most frequently are A sub 1. What's that stand for? That is first term. You're going to see A sub 1, you're going to see A sub n, which is the last term, or unknown term, yes, whichever way you want to look at it. Okay, so let me ask you this. What's A sub n minus 1? Is he right? He says the second to last term. If A sub n is the last term, minus 1 is the one before it. So if that was 10, then the one before it would be the ninth term. So when they want to say the one before it, they use a sub n minus 1. So if you were going to write a formula for the Fibonacci sequence and try to figure out, okay, how do I write this? Well, the Fibonacci sequence comes from doing what? Adding the two terms before you. So if they wrote that as a formula, they would say, okay, I want to find my unknown term. What terms do I need to add to get it? How do I write the one before it? The one before it's n minus 1. And then, yes, I would add the 2 before it, n minus 2. So in formula form, that's what the Fibonacci sequence looks like. Okay, if I throw that at you and just say, here, do this formula, you're going to look at that and go, what? Takes a little getting used to read that notation, to realize, oh, it just means the next to the last term and the one before that. You got to learn to read the notation. And that's kind of the trick to the game here. Okay, so the first part of your assignment, before we actually get into the different kinds of sequences, the first part of it is, oops, I'm saving over the calculus. I said oops. That's a not good thing. Pause a moment. All right. So our first goal here is, can we simply read this notation? It wants you to find the first 4 terms of this sequence using the formula. Okay, so they're telling you your unknown term is n. Consequently, if you want to find the first term, it means n is what number? If I'm going to find a sub 1, that means n is 1. So therefore, what number should you put in for n? You should put 1 in. So you're saying, what's 4 times 1 plus 2? 6. Okay, so then if it says find the second term, what should you do? There you go. 4 times 2 plus 2 is 10. And they're asking you for 4 terms, so you got to do this 4 times. So if n is whatever term you're on, so that's the number you're putting in for n here. Okay, this is one way they can write you a formula. Okay, do you see a pattern that happened there? Yeah, they added 4 every time. Why did it add 4 every time? You were multiplying by 4, and n went up 1 every time, so it's going to go up 4 each time. Okay, that's one way they can ask you to do this. The second way they can ask you to do this is what's called a recursive formula. Okay? We saw a recursive formula question on the new math assessment. Mr. Thomas and I both went, oh, really? I was shocked to see something like that on it. Okay, recursive formulas use a previous term to find the next term. So, yeah. Whereas over here on this first example I did, we were just doing what number term am I on the first term, the second term, the third term. Okay, this one's a little trickier, and you kind of got to see it to believe it. So let me give you one. Suppose I tell you your unknown term you're trying to find is a sub n minus 1 squared plus 1. Now, on a recursive problem, they have to tell you the starting value. So they have to tell you the first term, or this won't work. So I'm telling you the first term is 1. And this is where you got to learn to read the symbols. I want to find the second term. Okay, this formula is saying use what? What's a sub n minus 1? That's the term before it, because think about it. If I put 2 in there, 2 minus 1 would be, so it would be saying use the first term. So it wants you to use the term before you, which is 1, and what's it want you to do to it? It wants you to square it and add 1, which would mean you get 2. So when you want the third term, it wants you to take, n minus 1 means the one before it. It wants you to take that answer you just got and fill it in there. So that would be 2 squared plus 1, which would give me 5. So recursive formulas always use the previous number. So now it wants to get the fourth term.
5 squared plus 1.
Yes, I have to take the previous answer squared plus 1, which would be 26. And as you can see, this one's going to start to get big real fast. Because the next one's going to be 26 squared.
So if you wanted to find one like when it's right in the middle, you have to go through all that process to go all the way through.
Yeah, for a recursive formula, yeah. Without developing some way more advanced mathematics than we can go to right now. We'll put it that way. Okay. This is also that kind of, this particular one, sort of that same process I showed you with how they generate fractals with iteration, where they take the answer they got and they sub it in the function. They take the answer, they sub it in the function. That's a recursive process. Anytime you're using previous answers to get to the next one, it's called recursion. Okay, did that make sense?
Yes.
Yeah, all right. So this is a lot of this is terminology stuff. Where am I in time? Ooh, good place to stop.